All right, let's get right into it. Have you ever really thought about our planet's climate? I mean, not just as a list of facts about deserts or rainforests, but as one single, incredibly powerful, interconnected machine. Yeah, a giant engine that's been running for billions of years. So today, we're going to pop the hood and see exactly how this thing works. But first things first, we got to get our terms straight. You know, people throw around weather and climate like they're the same thing, but they're not at all. Weather is what's happening outside your window right now. It's short term. It's what you get. Climate, though, that's the long-term pattern. It's what you expect. So a rainy Tuesday, that's weather. A dry desert, year after year, that's climate. Simple enough, right? So here's the billion-dollar question. What actually fuels this incredible planetary engine? I mean, where does all the energy come from to create wind and rain and everything in between? Well, the answer is about 93 million miles away. It's our sun. The sun is the ultimate power source. It's the fuel that ignites the entire climate system. Without it, our engine wouldn't even turn over. Now, there's a technical term for all this solar energy, insolation. It's just a way of saying all the incoming solar radiation that's constantly bathing our planet. And you have to remember, every single weather event, from a tiny little breeze to a massive hurricane, starts right here with this energy from the sun. But here's the thing. This energy isn't spread evenly, because our planet is a sphere, right? The sun's rays hit the equator dead on, like a spotlight, delivering this super concentrated, intense heat. But up at the poles, those same rays come in at a really sharp angle, so the energy gets spread out over a much larger area. On top of that, our planet is tilted on its axis by 23.5 degrees. That tilt is the whole reason we have seasons. But no matter the time of year, this one simple fact, a hot equator and cold poles, is the fundamental imbalance that gets the whole engine roaring. Okay, so the engine is getting all this fuel, but how does it keep from overheating? Well, it turns out our planet has this brilliant self-regulating thermostat. It's all about balancing the energy that comes in with the energy that goes out. And here's how it works. It's a simple three-step process. Step 1, the sun's energy comes in and gets absorbed by the land and oceans. Step 2, the warmed-up Earth radiates that heat back outwards. And step 3, our atmosphere acts like a blanket. And this part is key. Basically, all of our weather happens in that very bottom layer, the troposphere. The gases in there trap some of that outgoing heat, which keeps us warm, while letting the rest just escape back into space. This delicate dance between incoming and outgoing energy, well, that's what creates Earth's heat budget. And it's this balance that keeps our planet's average temperature in that perfect little sweet spot that allows life, us, to thrive. For thousands and thousands of years, it's been a remarkably stable system. So we've got this uneven heating, creating a huge temperature difference. And in any engine, a difference like that creates pressure. And that pressure is what starts to turn the gears of our climate engine, creating what we call the Great Planetary Winds. This uneven heating creates these really distinct zones of air pressure around the globe. Think about it. At the equator, that intense heat warms up the air, which makes it expand, get lighter, and rise. This creates a permanent belt of what we call low pressure. But what goes up must come down, right? That air eventually cools and sinks back down around 30 degrees latitude. Sinking air is dense, and it creates a belt of high pressure. That whole loop is a massive circulation system called the Hadley cell. And guess what? The same basic pattern repeats further north and south, giving us the Ferrel and polar cells, and these predictable pressure belts all over the planet. And here is one of the most fundamental rules in all of physics, and it is the absolute key to understanding wind. Air will always flow from an area of high pressure to an area of low pressure. Nature is always trying to balance things out. And that one simple rule creates our planet's major wind systems. Air flows from that subtropical high at 30 degrees back towards the equatorial low. Those are the steady trade winds. Air also flows from that same high pressure belt up towards the low pressure at 60 degrees. We call these the Westerlies. And if you live in, say, North America or Europe, these are the winds that steer most of your weather. And finally, you've got cold air flowing from the polar high down towards that 60-degree belt, creating the polar easterlies. These are the giant spinning gears of our climate engine, constantly moving heat around the globe. But the atmosphere isn't doing all the work alone. The oceans, well, they're the engine's massive cooling system. Or maybe it's better to say they're the heat distribution system. They absorb incredible amounts of solar energy and then move it all around the planet. And think about this for a second. Water can hold way more heat than air can. It's not even close. This means the oceans are basically a giant heat battery for the planet. Ocean currents act like massive conveyor belts. You have the warm Gulf Stream, for example, carrying all this tropical heat up to northern Europe, which makes their climate way milder than, say, Canada's at the very same latitude. And on the flip side, you have the cold California current flowing south, bringing cooler, more stable weather to the west coast of the U.S. They are a huge climate regulator. And if you want to see just how powerful this ocean-atmosphere link is, you don't have to look any further than El Niño. This is just a periodic warming of the water in the tropical Pacific, but its ripple effects are felt globally. It can dramatically weaken the Indian monsoon, that vital seasonal wind shift that brings rain to South Asia, and cause terrible droughts. But at the same time, it can cause devastating floods in South America. It's the perfect example of how a small change in one part of the climate engine can throw the entire system for a loop. So the sun provides the fuel, the atmosphere and oceans move all that heat around. So what's the output? What does this engine actually produce? Well, the answer is all the weather we experience every single day. And let's look at one of the most important outputs, rain. So the most direct type of rain is convectional rain. This is super common in the tropics. Basically, the sun just beats down on the ground, heating it intensely, which causes the warm, moist air right above it to shoot upwards. As it gets higher into the cooler parts of the atmosphere, that water vapor condenses into clouds, and eventually you get heavy rain, usually in the form of a big afternoon thunderstorm. It's a direct result of that initial solar heat. Next up, we've got orographic rainfall. This is what happens when those planetary winds we talked about push moist air smack into a barrier, like a mountain range. The air has nowhere to go but up, and as it rises, it cools, and it has to drop its moisture as rain. Think of the massive rainfall on one side of the Himalayas, or why a city like Seattle gets so much rain from Pacific air hitting the mountains. This also means the other side of the mountain stays dry, creating what's called a rain shadow. And finally, there's cyclonic rainfall. This is the rain you get from big storm systems. Remember those low-pressure belts? Well, in any low-pressure system, air is spiraling inward and upward on a massive scale. This huge, widespread uplift forces enormous amounts of moisture to condense, and that causes the long, steady, widespread rain we get from those big storms that can last for days. And that brings us to the cyclone itself. Really, a cyclone is just a fancy name for a powerful, organized, rotating, low-pressure system. All of that air spiraling inward and shooting upward is what creates the intense winds and the heavy, heavy rain we associate with major storms like hurricanes and typhoons. It is one of the most dramatic and powerful outputs of the entire climate engine. And just to complete the picture, the exact opposite is an anticyclone. That's a high-pressure system where air is sinking towards the ground. Sinking air actually warms up, and it prevents clouds from forming. And that's why high-pressure systems almost always bring us clear skies and calm, settled weather. So, here we have this incredible, self-regulating engine that has shaped our entire world for eons. But for the very first time in planetary history, one species, us, is actively tinkering with the settings. And this, right here, is why understanding how this engine works truly matters right now. Let's go back to our planet's thermostat for a second. That natural greenhouse effect is absolutely essential for life. Without it, Earth would just be a frozen ball of ice. The problem is, we are adding more greenhouse gases, especially carbon dioxide, into the atmosphere. This enhances the effect. You can think of it like we're thickening the planet's blanket. The basic physics are exactly the same, but now more heat gets trapped and the whole system starts to warm up. And so we're left with this absolutely critical question. Our climate engine has maintained a remarkable stability for thousands of years, which allowed our civilizations to grow and flourish. So what happens? What happens when we fundamentally start changing the settings on an engine this powerful, this complex, and this vital to our very survival?